So today's lecture we will discuss about the nuclear reaction and what are the various type of a nuclear reaction, and then we will discuss about the Q value of a reaction, so which tells us about the exothermic or endothermic type of a nuclear reaction. And then we will discuss about this natural and artificial transmutation, and do some examples related with this artificial transmutation problem. And then we will discuss in detail about this nuclear fission phenomena, and how these nuclear reactor they work, and what are the role of moderator, the cadmium rods, and how these fission, spontaneous fission it happens actually. And if time pertains, then we will also discuss about this nuclear fusion, or otherwise we will continue this fusion process in detail in our next lecture. So let us start with the simple nuclear reaction. So the first induced nuclear reaction, it was accomplished by none other than this Australian scientist, that is Rutherford, who gives the famous alpha scattering experiment. So who bombarded these alpha particle with the heavy target, solid target nuclei, and he see that these alpha particles they are being scattered at different scattering angles. And he discovered these nucleus which is present in the center of the atom. So from his experiment, with the experience of the experiment which he has done with these alpha particles, so he thought that the alpha particle, so they might have the power. So if he is shooting those alpha particle with a very high energy, so that it can breach these nuclear boundaries, so that it can bombard also these nucleons from this nucleus. So this is finally he is able to succeeded, and he did it. So the first artificial transmutation, so when he shoot these alpha particle to these nitrogen molecules, and he see that the oxygen atom along with that proton, so it is being formed. So after that, many scientists they get the idea of these artificial transmutations, and many people so they try to work like the formation of gold. So how you can make such costly metals from this cheaper, but this idea is still going on, and there are many type of these artificial transmutations. So people are doing experimentally. So we will discuss it in detail after a few slides. So let us discuss some of the types of a nuclear reaction. So first type, that is the elastic scattering. In elastic scattering, the particles they are scattered in a different direction without any losing their energy. So the residual nucleus, it is the same as the target nucleus. Here the residual nucleus, it is generally considered as the daughter nucleus, and it is left in the same state. So it can be represented something like this type of reaction, where the parent and daughter nucleus, it is the same. So this is the example of this elastic scattering. So the direction of these particles, so it is being changed, but their kinetic energy it remain conserved. So the second type of scattering of this nuclear reaction, that is the inelastic scattering. So in this inelastic scattering, the particles they are scattered although in different direction, but with different energy. So there can be lose or gain of the energy. So energy of this gain or lose, it can be due to this collision. So the residual nucleus, which is the same as target nucleus. So the nucleus, it when interact with this shooting particle, it reaches into the excited state, and further this excited nucleus, it can be broken down into some other nuclei. So this is generally considered as the compound nucleus. So there are many examples of this inelastic scattering, like when we are shooting these high energy neutrons with this uranium-230 8. So that is the famous example is of a nuclear fission. So in this inelastic scattering, the compound nucleus which is formed, that is in the excited state, and it can break up into many nuclei, or it can break up into two nuclei. So depending upon the energy that excited nucleus it is carrying. So next example of a nuclear reaction is radiative capture. In radiative capture process, the incident particle, it is being absorbed or captured by this target nucleus, and this target nucleus, when this capture this incident particle and it goes into the excited state, that is generally considered as the compound nucleus, so which further disintegrate to produce one or more gamma photons. So this is something like this nuclear fission reaction, when this uranium 235 it absorbed these neutrons and it converted into uranium 236, which is considered as the excited state and generally known as the compound nucleus, and it further break up into two small fission fragments. So the next type of example is the transformation reaction. So in this incoming particle, it is being absorbed by this nucleus, and the compound nucleus which forms, it emitted different particle. So you can see in this example, so when this alpha particle, it is being bombarded with this beryllium, and there is formation of compound nucleus, and when this compound nucleus it further break up into this carbon 12, along with that this neutron it is being emitted. So the particle which is emitted is different as the particle which is being absorbed. So these are the examples of a transformation nuclear reaction, and there are many type of transformation reaction. So for example, we are shooting these neutron particle, so in this nuclear scattering, and we are shooting proton with this the nuclear interaction, so the formation of other particle, that representation, so that is the representation of these transformation reaction. So another type of a nuclear reaction, that is the photodisintegration. So as the name suggests, in this photodisintegration, a very energetic photon it is being absorbed by this target nucleus. So this reaction, so the symbol it suggests that the X, these and the first particle which I have written in this bracket, so that is considered as the reactant, and this second particle, so that is again the gamma photon which is being emitted, and this Y, so these two, so they are generally considered as products, and these two they are generally considered as reactants. So sometimes they do not write this full nuclear reaction equation, so they just write these in this symbol form. So you must be familiar with this notation, that how you can see this equation into a full nuclear reaction. So this is the example of photodisintegration, that this photon it is being absorbed, and the particle which is emitted is a proton, and along with that this neutron it is being emitted. So similarly, this photodisintegration it can emit many type of different particles. So it can be a proton, it can be alpha particle, so and so. So depending upon what type of parent nucleus with which it is being absorbed. So next is the stripping reaction. So in this stripping reaction, one or more nucleons from the projectiles they are captured by this target nucleus, and the remaining stripped nucleus it is emitted in a different direction. So you can see that this target nucleus copper it can capture more than one nucleons, like it can capture proton or neutron together, and it can be converted into some other nuclei, or it can emit some other particle. So these are the stripping type of reaction. So direct reaction, it is simple. There is no formation of any compound or excited state of nucleus. So this is you can see that carbon, it is absorbing this proton, and it is being converted into the isotope of carbon 612. Along with that, this deuteron, deuterium, it is being emitted. So in this compound nuclear reaction, you can see that a compound nucleus, it is being formed between this reactant and products. Since this compound nucleus, it has a very short life period, so that is of the order of 10 raised to power minus 10 to 10 raised to power minus 16 second. So once the compound nucleus, it is formed, it forgot its previous history, how it is formed, and further no one knows that this compound nucleus, it will break into which type of product nuclei. So there are many type of these compound nuclear reaction. So it is not likely that this fluorine which is formed here as a compound nucleus, it will only converted into this oxygen or proton. So there are chances it can split up into some other isotope oxygen. Along with that, this deuteron is being emitted. So no one knows. So it is there are how this deuteron is formed, within how much time this deuteron is formed, and depending upon the nature of this parent nuclei. So there are some consequences on which this compound nucleus, it is show its dependency. So next is the Q value and the threshold energy of this nuclear reaction. Now, in order to have any nuclear reaction, so the law of conservation of energy and law of conservation of a linear and angular momentum, it should be satisfied. Along with that, the law of conservation of charge. Now you can see in this reaction, this small x bombarding nuclei, it is being targeted with this parent nucleus, and these are our products. So small y, so it is our outgoing particle, and capital Y, that is our product nucleus. Now, so everyone, so you can see that this capital parent nucleus, it is in the state of rest. So you can see that this bombarding particle small x, it has some sort of rest mass energy and some kinetic energy. Along with that, with which energy it is being shooted with this parent nucleus. So this is the energy of our parent nucleus, and these are the total energies of our outgoing particle and our parent nucleus. Now the value of this Q energy, so it is equal to Ey plus Ex. So here it is Ey plus Ex minus Ex. You can see that. So this is equal to these masses of this parent and daughter nuclei. And depending upon the Q value of this nuclear reaction, so if Q value is positive, so what does it mean? So it is said to be exothermic, that the energy, it is being released from this nuclear reaction. So if Q is negative, then the reaction is known as this endothermic reaction. So from this you can calculate the kinetic energy of this incident particle, or kinetic energy of this bombarding particle. So you can calculate kinetic energy of each particle from this Q value equation. So sometimes there are numerical problems which comes. We will also try to solve one or two numericals related with these Q values. So next is the transmutation. Now in natural transmutation, till now we have discussed only those transmutations of the nuclei to another by emitting some radioactive particles. So the radioactive nuclei, so they are the best example of a natural transmutation. So when they are decaying some sort of these alpha, beta or gamma radiation, and they are converted into some other daughter nuclei, so they are the example of natural transmutation. Apart from that, there are many things like we are doing in this laboratory in order to have these artificial transmutation. So in this conversion of one element to another element, it is done artificially. So artificially means we are bombarding bombarding particle to our target nucleus, and then we will see that what are our products. So it is just alchemy, and depending upon so how this reaction goes. So you can see from this best example of this nitrogen when it is bombarded with this neutron. So this product of nitrogen from carbon, it can happen both way. So it can happen artificially, so we can generate these carbon in the laboratory, or it is also happen this with this natural transmutation. So because this nitro, there are number of free neutral particles so which exist in this space, and when they are interacting with these nitrogen and a lot of carbon which is being formed. So here is another induced transmutation example that has been successfully accomplished. So you can see that we can bombard these proton to this mercury atoms, and from that we can generate or form this gold atom, along with that this helium nucleus. So this is the famous or the best achievement of this human. So the man's striving to generate as much as gold they can generate from these artificial transmutation. But what is the driving force which can lead to such type of chemical reaction? So for this we need a large number of accelerators which can accelerate this proton to so much high energy so that it can deeply penetrate to the nucleus of this mercury to form these gold molecules and atoms. So therefore the accelerator and these formation of high energy accelerator and detectors, it is a very costly as compared to the price of gold. So it is not an easy task so that we can easily generate gold. So otherwise everyone tries to run in these type of chemical reactions, because in order to form these accelerators, like you can see, this is the picture of this large hadron collider which is situated in this CERN, in CERN Geneva, which is in the border line of France and Switzerland, and it is a quite huge costly project. So a 27-kilometer underground tunnel it is being formed, and there are 4 accelerator or control station you can see, and which are controlling or shooting these high energy protons and other particles, and they are looking at how these particles they are interacting. So it is a very costly project. So there are various mechanisms with which we can do these artificial transmutation. So first example is this artificial transmutation by proton. So this P alpha, it is represent that our parent nucleus, it is being bombarded with this proton, and the alpha particle, it is considered as our outgoing particle. So lithium, it is being bombarded with this proton, and this beryllium, which is formed as a compound nucleus, and when it loses its energy, and it is being converted into 2 helium molecules. So there are many other examples with which we can form these artificial transmutation, like this proton neutron nuclear reaction, proton deuteron nuclear reaction. So we can do these artificial transmutation by capture of this proton. And so second way we can do these artificial transmutation is by this transmutation by these neutrons. So there are transmutation reaction for this neutron and alpha reaction. So third way we can do this transmutation by this deuteron particle. So there are many ways we can do such type of nuclear reaction. So how we can say that this nuclear reaction, it is a feasible nuclear reaction. So here you can see it is the example of a nuclear reaction. So this polonium, it is being converted into lead and alpha particle which is being liberated. Now how you are able to tell that whether it is a valid reaction or it is a violated reaction? So there are first point, you will see that you will check that whether this nuclear reaction, it is following these conservation laws, or whether it is balanced on both sides of reactant and products. So second point, you will see the conservation of nucleons. So the total number of nucleons that is within these reactants and products, they must be same. And the second is you can see the conservation of charge. So you can see that total nucleons, that is 214 on this side, and the products, that is 210 plus 4, that total is 214. So it is equal on both sides. And second, you can see the conservation of charge. So whether the total charge, it is being conserved within this reaction. So charge is also conserved, you can see. So here is another example of this nuclear reaction when this carbon, it is undergoing beta decay to form these nitrogen molecules. So how you can construct this nuclear reaction and how you can balance this nuclear reaction? So there are two tasks. One, you need to construct a nuclear reaction, and second is you need to balance these nuclear reaction. So first, you will see the conservation of nucleons, it should be equal. So the second, you will see the periodic table for the carbon, it has a 6 atomic number, while for nitrogen it has a 7 atomic number. So you can write here 6, here 7. So total mass, it is being equal on both sides. So what is that particle which is having this -1 and 0? So this is considered as a electron. So this is how you can balance a nuclear reaction, and you must be able to tell what will be the smallest particle which will emit when this reaction will happen. Now here is you can see that whether there is a conservation of charge or not. Now since carbon, it has 6 proton and 8 nucleons, so charge, it is equal to the spin is 0. So you can see that total spin, it is having a 0 spin. So nitrogen, you can see that with this Nordam rule, so it is equal to 0. So this electron, which is having a half integral spin. So if you look at this reaction without this anti-neutrino, so it is not following this conservation of laws. So that's why this Enrico Fermi, so it gives us the idea that there is a formation of another particle that he gave the name neutrino and anti-neutrino. So basically the idea of this neutrino hypothesis, I will just tell you some important points about this neutrino hypothesis. So they get the idea from this solar neutrino. So you can see that when this proton within the sun, they are interacting with protons and helium is formed, and along with that the positron, they are emitted, and along with that the neutrino particles, they are emitted. And you can see that we are facing a large number of neutrinos. So our body, so 10 raised to power 14 neutrinos, they are passing from our body per second, but it do not affect. Why this neutrino particle, it do not affect our body? Because it is a massless particle. and it is a chargeless particle. So it do not have any mass or it do not have any charge, so that's why it do not interact with this matter, and if it do not interact with the matter, it will not ionize the matter through which it passes. So it is very difficult to detect neutrinos, and this neutrino discovery which has been done by this two American, that is the Roy, Rayne and Cowan. So in 1956, so with which they get this Nobel Prize for the discovery of this neutrino. So that's why for this beta decay, you can see that the spectrum of this beta particle, it is a continuous spectrum. So because the energy which is being shared by these two particles, so if the total energy of the reaction, it is always conserved. So if one particle it is having less energy than the another particle like a neutrino, it will enhance its energy in order to conserve the total energy. So the next nuclear reaction you can see, so in the laboratory when aluminium nuclei, they are bombarded with this alpha particle. So this is the reaction. So the question is, this reaction is an example of nuclear fission, nuclear fusion, natural radioactive decay, or artificial transmutation. So students, what is your answer? Hello.
Yes, sir.
So what is the answer of this question? So it is artificial transmutation. So in the transmutation, we have discussed that we are shooting some small energy particle, and we can convert one parent nucleus to another daughter nucleus, and along with that some small particle which is being coming out. So it is not an example of a fusion, it is not an example of a fission rather, and it is not a natural radioactive decay. In a natural radioactive decay, we do not need to bombard any bombarding particle. So the only example which it is showing, it is the example of artificial transmutation. So let us do one more example. So when a high energy alpha particle, so it is collided with this aluminium nucleus, a nucleus of phosphorus may be produced. So which of the following equation correctly show this artificial transmutation? So what is the correct answer, students?
It's for first one.
Which one?
A.
Yeah, so you can count like here 13 plus 2, that is 15. So right hand side it is 15. 27 plus 4, it is 31. So here 30 plus 1, so it is 31. So conservation of nucleon and conservation of charge, it is followed. So option A is the correct answer. So otherwise you can do this elimination method, because helium it is having 2 proton and 4 neutron, 4 mass number. So here it is written 1:2, so it is wrong. So here it is also wrong. So you can eliminate this and this, and along with that here it is written proton. So proton do not have a 0 number, so you can also eliminate this proton. So only option left is option A. So next question is, when the isotope of aluminium it is bombarded with this alpha particle, the following nuclear reaction it takes place. So we are bombarding this aluminium with this helium alpha particle, and these are our products. So what is the value of this X? So what is your answer?
So first one is correct answer.
Yes. So first of all, you need to find out what is a neutron. So neutron, it is one nucleon and zero charge. So when you write out neutron, so the left side has 31 nucleon, you can see. So 27 plus 4, 31 on left hand side. So here it is 1, so it has nucleon number should be 30, and you can see proton number is 13 plus 2, so it is 15. So option A is the correct option for this question. So next example is the isotope of sodium. It undergo radioactive decay to the stable isotope of magnesium 24. So complete this nuclear reaction for this decay. So this is a radioactive decay, so it is a natural transmutation. So how you will complete? So what is the second particle which is being emitted here?
It is positron and neutrino.
So any other students? It is not positron, it is electron, because here is 12, so it should be -1. So -1 is electron. So this is beta minus decay. So this is an
Yes.
example of beta minus decay. So not positron. So there should be electron
Antineutrino.
and antineutrino. So this is how you must be familiar with these any type of a nuclear reaction. If it comes, then you should be able to tell. So what will be the bombarding particle? What will be the outgoing particle? What will be the daughter nucleus? What will be the parent nucleus? So next example is the process of orbital electron capture. So this is generally known as a K capture. So here orbital electron capture is that phenomena. So let us say this is our nucleus, and if this nucleus it is in the excited state, and it should have that much of energy, and the energy, if it is greater than the binding energy of these orbitals, so these are our orbital atomic orbitals. So in this first k orbital there are 2 electrons, in this p orbital there are 8 electrons. So if the energy of this excited nucleus it is greater than the binding energy of this k orbital electron, then there is the probability that this nucleus it will capture this electron within itself. So it will capture its electron, and then there is the formation of hole. So this process of capturing of orbital electron by these high energy nucleus, so that is known as the orbital electron capture. And there is more probability that it will capture these k orbital electrons. So there are examples of also been seen for this L orbital capture and M orbital capture, but they are very rare. So the probability of k orbital electron capture it is very high as compared to this L orbital or M orbital. So this example says that in this k orbital electron capture process, so when a nucleus capture an electron from this innermost shell of electron which is surrounding this nucleus, and you can see that when a k capture occurs in this iron nucleus, the nucleus is changed into manganese. So iron nucleus, it is capturing orbital electron and it is converted into manganese. So which equation that represent this nuclear reaction? So yes, students, what is the correct?
Sir, I think option C is correct.
Yes, because when this electron it is being absorbed by this nucleus, you can see that the total nucleons here it is electron. So first of all here charge is given positive, so this cannot be the correct answer. So here electron, this cannot be the correct answer. So here you can see a 51. So electron, it do not have this +1. It is so this cannot be the correct. So the only option you can see, so this formation of this manganese, which is with this 25 atomic number. So in the word of this nuclear reaction, we have to keep very precise track of this mass of the nuclei and how this mass it is being converted into the energy. So generally we use this Einstein mass energy relation in order to find the mass defect of a nucleus, and from that mass defect we generally find out the binding energy, and from that we can able to tell that whether it is having a Q positive value or a Q negative value. So what is this one atomic mass unit? So one atomic mass unit is 1/12 of the mass of one atom of carbon 12, which is having 6 protons, 6 neutron, and 6 electron. And the value of one atomic mass unit, that is equal to 1.67 into 10 to the power minus 27 kilogram. So the correct option for this one unified atomic mass unit, that is equal to 1/12 of the mass of one neutral atom of carbon 12 nucleus. So in order to find this how much energy is being released from this particular nuclear reaction, we generally use this Einstein mass energy relation. So this tells us about how much energy it is releasing, or how much energy it is being absorbed for a particular nuclear reaction to happen. So this is very interesting problem you can see. So the question is, how many students does it take to power a light bulb? So how you will solve this? So do you want to know your worth? So how much energy you are carrying with yourself? So, and it is very easy to figure out. So let us take an average student which is having a 70 kg of mass. So when we turn this mass into energy, so using this E is equal to mc square, and this comes out to be equal to 6.7 into 10 to the power 18 joule. And from that we can find out the power, that is rate of energy with this rate of change of work done, or you can say energy over time. And so time, if we consider the power of a light bulb, that is around 60 watt, and from that we can find out the value of this T. So the energy from a student, it could lit up a 60 watt bulb, that is for these 200 billion years. So if we try to extract energy from a single student, and it can lit up this 60 watt bulb for these much time, and now you wonder how much energy you are carrying within yourself. So we generally say that everyone, it is made up of matter. So human body, it is carrying a huge amount of energy. So second, we can convert this atomic mass unit in terms of mega electron volt. So that is of the order of 931.5 mega electron volt. So there are two type of problems which we generally find out. From that we can find the binding energy. So the generally mass defect, it is the difference between the mass of this nucleus and the sum of masses of its isolated nucleons. So mass defect, it tells us the transformation to energy according to this Einstein equation, and is released in forming the nucleus from its component particle. So binding energy is the energy that is required to separate the nucleus into its individual nucleons. So this is opposite. So mass defect, it is showing, so we need to that much energy to separate a nucleus, that is binding energy. And if we want to combine those nucleus, then we need to have this delta M, it should have a positive value. So this is another one example of this nuclear reaction, which will tell us about the mass defect and the binding energy for this particular nuclear reaction. So these two proton, they are interacting with these two neutron, and helium, it is being formed. So these are reactant and these are products. So the table, it is showing the atomic mass unit of electron, proton, hydrogen, neutron and helium atom, and using this find the mass defect of this nuclear reaction. So you can see that the total number of nucleons within this reactants, there are two protons and two neutrons. So proton, that is atomic mass unit, which is 1.007. So this is atomic mass unit of neutron. So total atomic mass of this nucleons, that is 4.032, and this is the atomic mass of our helium nucleus. And you can see that the mass defect, so how much mass of this nucleus which is formed, it is having less value, that is of the order of very very small, 0.0303 atomic mass unit. And when we find out this how much energy it is being released in this nuclear reaction, so you can see that when we find out the binding energy, which is equal to mass defect into c square, so this much of energy which is being released for this nuclear reaction. So in order to pull apart this helium and separate it into its constituents, we need 28 mega electron volt energy, which can separate these helium into two proton and two neutron. So similarly, you can see that in order to have disassembling this helium, we require energy. So if we want to disassemble this helium nucleus, so if we supply this much of energy, then we can break this helium into two proton and two neutron. And on the other way, so the reverse is the same yield of this energy which is being released. So when we interact these two proton with these two neutron, and this much of energy which is being released. So on the other way, so that is one and the same thing. So the amount of energy which is required to have a reaction, that is equal to amount of energy which is required to break that particular nucleus. So these are some of the examples of alpha and beta decay. So everywhere you can see that how much energy it is being released, and that is generally converted into the kinetic energy of those particles which are moving at very high energy. So this is the binding energy which is formed, and this energy, it is being carried by these alpha particle as their kinetic energy. And similarly, this particle energy, it is being carried by these beta particle. So this is for your practice. So a reaction is given, you have to find the binding energy of this, how much energy it is being released in this particular nuclear reaction. So as I have told you, so first of all we need to calculate this mass defect, and from this mass defect we can find out the amount of energy which is being released for that particular nuclear reaction. So in a nuclear reaction, so the mass defect, it can have a plus value or it can have a negative value. So if the delta M value, if it is greater than 0, so what does it mean? If the mass of reactants, it is greater than the mass of products, in that case the energy will be released. And if the value of this delta M, so that is the mass of this reactant, it is less as compared to mass of products, so in that case we require energy in order to undergo these nuclear reaction. So this is very very important slide. So you need to check how you can find out whether these reaction, so energy is being released or we require energy in order to have this nuclear reaction. So you can check from that calculating these mass defect values. So from this mass defect you can calculate the binding energy, and from that you can calculate the binding energy per nucleon. So if we divide that particular with respect to their total number of nucleons, how much they are carrying. So this is we have already discussed in our previous lecture, so I have talked in brief. So this curve, it tells a large number of things, that the most stable isotope, that is our iron, so which is the most stable element. So the bigger the binding energy per nucleon, the more stable an element is. So in this binding energy curve you can see that this iron, it is having the highest binding energy per nucleon, that is of the order of 8.7 mega electron volt. So iron, it is the most stable element in our periodic table. And what is the binding energy of this uranium 238? So how you can calculate? So you can calculate this binding energy per nucleon of this uranium 238. So that is of the order of 7.6 mega electron volt. Or you can calculate it the other way around. How many uranium 238 it is having the total binding energy? So since uranium 238, it has 238 nucleons, and the binding energy of one nucleon is 7.6 mega electron volt. So therefore one uranium atom, it has an energy of around 1800 mega electron volt. So that's why huge energy it is being released when there is a nuclear fission reaction. So second, what is the mass defect of this uranium 238? So if we assemble it from scratch, so mass defect, it is equal to binding energy. So binding energy, so that is we can convert it from this 1800 mega electron volt to mass. So how we can convert it? So we divide this with the 931.5, and this comes out to be 3.21 into 10 raised to power minus 27. So this is the mass defect. So nuclear fission, so this is the very important type of a nuclear reaction, so which has quite a potential application in order to have this 21st century energy production. So there are number of laboratories like Rutherford Appleton laboratories in Rutherford or Oxford University. One is in Daisy in Germany. One is in Lawrence Livermore in United States of America. So there are laboratories which are trying to undergo this nuclear fission phenomena in the laboratories, and they are trying to maintain or trying to generate this much of energy. So the biggest problem is how we can control this huge amount of energy. So nuclear fission, this is first given by this Fermi, so who performed this nuclear fission reaction. So he considered the sample of uranium 235 and bombarded it with the neutron, and what he see that there is formation of this compound nucleus, and when this compound nucleus, it breaks down, it converted into barium and krypton, and along with that these are three neutrons which are being released. So this reaction, it is the best example of nuclear fission reaction, and the heavy nuclei, it is being broken down into lighter nuclei. And if there is this compound nucleus, if it is broken into many like 10 to 20 small fission fragments, then that the nuclear reaction is known as sepalation reaction. So if it is broken into two small fission fragments, then it is a fission reaction, and if it is being broken into more than two small fission fragments, then it is a sepalation reaction. So in this nuclear fission, the large nucleus, they are more favorable as compared to small nuclei. So the total binding energy you can see from this binding energy curve. So the nuclei which lie within this range, they are undergoing this nuclear fission more favorable. So the binding energy would increase, which means that the daughter nucleus which are formed, they are more stable than the parent nucleus. So the excess energy which is released by this reaction, so that is being carried out by these fission fragments and the neutrons which are coming out. So the spontaneous fission, that is the chain reaction, it is very very rare. So uranium is the largest nucleus which is found on earth, and its isotopes will sometimes fission naturally. So you can see that the half-life of this uranium 235, it is very very large, but this is we generally use fissile material. Fissile material, that is the mixture of uranium 235 and uranium 238 in our nuclear reactors in order to undergo this nuclear fission phenomena. Otherwise this uranium 235, it can trigger this nuclear fission even with a neutron which is having a 1 mega electron volt of energy, and that is more likely that it is very very difficult to control. So that's why we generally mix these our fission material with this uranium 238 in order to make a controlled nuclear fission reaction. So the bombarded nucleus with these neutron, they can trigger this fission fragment. So you can see that this is the reaction. So when uranium, it is hit by a neutron and it is being captured, and it becomes excited and unstable, and it quickly, so this is, it quickly breaks so into these selenium and xenon. So the stronger, so what is the physics behind this nuclear fission? You can see that the stronger forces that hold the nucleus together, only they act over for a very short distance. So when a uranium nucleus, it absorbs a neutron, so it knocks the nucleus out of the shape, and it tries to undergo large number of deformations as we have discussed. So there is a large number of rotation and vibrations, and due to these deformation, the electrostatic repulsion, so due to these protons which are present within the nucleus, so these electrostatic repulsion, it becomes greater, and these large nucleus, it split up into two small nucleus. So so this was triggered, and you can see this is the exponential growth. So one reaction, it is being forming these two neutron. When these two neutron, it further interact with the, please mute your mic, someone mic is on, please mute your mic. Just 5 more minutes, then we will close it. So you can see that these two neutrons, so they further trigger, they further interact with these two uranium, and they form four neutrons. These four neutrons, they interact with the uranium atom and for 8 neutrons. So this is how this reaction once triggered, and it is very very difficult to control, and there is a very very large number of neutrons which is being formed within a fraction of second, and if we do not control it, so then it can explode our nuclear reactor. So there are two type of nuclear fission reactions. One is uncontrolled chain reaction, so that is not controlled, and the second is, mute your mic, so please mute your mic. So in this uncontrolled chain reaction, the reaction is uncontrolled, and it is very rapid. And basically it depends upon this multiplicity factor. So the multiplicity factor, that is the number of neutrons which are hitting the next target over number of neutrons which are being emitted. And this multiplicity factor, it is generally represented with k, and if k is greater than 1, then it is a uncontrolled chain reaction. So you can see in this uncontrolled chain reaction, so a large number of neutrons, they are very formed in a fraction of second. So these three neutrons are formed here. Uh, there are 9 neutrons, 3 from each uranium. So there are 27 neutrons. So a large number of neutrons, since our fissile material, it is having large number of uranium atoms. So it becomes a very a spontaneous chain reaction, and it can destroy our nuclear reactor. And there are some incidents which have been seen in Ukraine, so where the fission reactor, it has been exploded due to some negligence. So second way, we can form our nuclear reactor as controlled nuclear reactor. So there are two ways with which we can control these nuclear reactors. So one way is we can control these nuclear reaction using the control rods. So you can see we using these cadmium or boron rods, and these cadmium rods, they absorb these extra neutron. So this is the neutron when it is interacting with this uranium. So these are barium and krypton which is formed, and along with that these 3 neutrons, they are formed, and these 2 neutrons, they are being absorbed by these cadmium rods. Only 1 neutron, it interact again with this uranium atom, and again you can see that 3 neutrons, they are formed, and every time these rods, they are absorbing these extra neutron. And this is how we can make this nuclear reaction a controlled nuclear reaction. So in this controlled nuclear reaction, this multiplicity factor, the number of neutron which are hitting the target, so that must be equal to number of neutrons which are being formed. So the value of this multiplicity factor, if it is equal to 1, so then it is a controlled chain reaction, and if it is greater than 1, it is uncontrolled, and if it is less than 1, so what does it mean? So our nuclear chain reaction, it will going to soon end, because there are not so much number of neutrons which are formed, and our fission reaction will stop in this case when k is less than 1. So the second is the role of moderator. It is very high. So this moderator, so they try to absorb this extra energy of these neutron and try to slow down the energy of these neutron. And you can see that the common used moderator, so which is having a high absorption coefficient like water, heavy water, or graphite, which we use. And since the extra energy, it is being absorbed by these moderators, so the water temperature, it becomes very high. So that's why most of the nuclear reactor, they are assembled near the sea or a big river, where we can use that extra amount of water in order to slow down these, or release the extra energy which is being absorbed from these neutrons. So this is I have explained how these rods we can insert. So this is our uranium fuel, and we can control these cadmium rods. We can insert it up to what extent where we want. So if we insert these rods completely, then our nuclear reaction, it will stop. The second way, so this is very important. So the second way we can control this nuclear reaction by adding this boric acid as a coolant. So the extra boron atoms which we have added along with this uranium fuel, you can see that these boron, they absorb these neutrons which are being formed, and these boron they started to convert into lithium and helium. So since this neutron it is being absorbed, so there is no longer any neutron which will interact with this uranium fuel, and our nuclear reaction it gets stopped, or we can control it depending upon how much percentage of boric acid we add it as a coolant. So this is the numerical related with this. You can see, so the calculate the energy released by this nuclear fission from 2 gram of uranium in kilowatt hour. So we have to find 2 gram of uranium release how much of energy. So energy released per fission, we know that when one neutron it interact only approximately 200 mega electron volt of energy is being released from one uranium atom. So that is equal to this much of energy in joules. So total energy number of atoms, so that is 200 into 10 raised to power 6 into 1.6 into 10 raised to power minus 19 converted into joules. So number of moles, that will be equal to mass over molecular weight. So mass is 2 gram, molecular weight of uranium is 235, multiply by Avogadro number and multiply by this total number, and this is, you can see that 2 gram of uranium releases approximately 0.45 into 10 raised to power 5 kilowatt hour of energy. So kilowatt hour generally it is represented as 1 unit of energy. So our electricity bill, so it generally come in terms of units. So for example, if you are consuming a 10 megawatt 10 kilowatt hour of house electric power, and approximately your bill for 1 month, that is around 500 units, and 500 unit means 500 kilowatt hour, and this is your consumption of 5 to 6% for 1 month. And now you can compare, so we can generate 10 raised to power 5 kilowatt hour of energy from 2 gram of uranium. So this is very huge. So it can solve our electricity problem, that is for the 21st century energy production. This is a big challenge for our experimentalist, how we can efficiently control this much of energy, so that we can preserve our resources like coal and petroleum and use this energy. But there are some disadvantages of this energy, because these high energy neutrons, so they need to be controlled. So if we do not control these high energy neutron and they get leaked from these reactors, so then it can be dangerous for this human life, which can cause severe problem up to many generations. So this is a very dangerous project, but we need to have, if it is under control, then we can use this energy. But nuclear fusion, which is more advantages as compared to nuclear fission, so that we will discuss in our next lecture. So this is all about for today's lecture. So in our next lecture, we will discuss about nuclear fusion and some particle accelerator, and we will try to cover this nuclear physics by our next lecture. So then in the next 2 lectures, we will cover the particle physics syllabus. So probably more 3 lecture I will take for this, 1 for nuclear physics and 2 for particle physics. So any doubts? The session is open for questions.
Sir?
Yes.
So in a fission reaction, what is multiplication factor of neutron?
In a fission?
Yes, sir. In fission reaction, what is multiplication factor of neutron?
So multiplication factor, so that I have told you. So if you can see in this slide, so just a minute. So far a controlled nuclear reaction, the multiplicity factor is 1. So you can see, so if the value of K is 1, so multiplicity factor is equal to total number of neutron which are being ejected over total number of neutrons which are being formed. So K is equal to 1 means that our neutrons which are under controlled in our fission reaction. So the, for example, if I am shooting 100 neutrons which are interacting with this uranium, and for one reaction there will be 300 neutrons which will be formed after the first stage. But what I am doing is I am controlling those 200 extra neutrons, and I am sending only 100 neutrons which will go in the second phase and they will interact with this uranium. So K value, number of neutrons which are interacting over total number of neutrons which are formed. So when this K is equal to 1, so then we can say this is our controlled chain reaction. So if our neutron number it increases, so in that case the value of K it becomes greater than 1. So in that case the number of neutron it increases exponentially, and if we not control it at appropriate time, either through moderators or through cadmium or these coolants, then our nuclear reactor it can explode. And for example, if I want to stop my nuclear reaction, so what I will do is I will insert all those control rods completely, and those control rod they will absorb our neutrons which are being formed, and in that case the value of this K it becomes less than 1, and ultimately our nuclear reaction it will stop. So these are the three conditions. So this is for controlled nuclear reaction, this is for uncontrolled, and this is if I want to stop it. Is it clear?
Yes, sir. Very well.
Okay. So any other question?
No, sir.
So okay, dear students, so see you in the next week with the 2 lectures. So till then, goodbye.